Okay, our next section is about the stoichiometry of reactions in aqueous solution, the fundamentals. And the goal is to use stoichiometry principles for reactions occurring in solution. Okay, so let's look at the fundamentals. So normally when we talk about stoichiometry, we use masses. So if you want to go from the grams of A to the grams of B, you can't do this directly because it's very difficult. In a balanced reaction, it doesn't represent, the coefficients do not represent masses, they represent moles. So if you want to go from A to B, you have to go from moles to moles, like we see here. So how do you go from grams of A to moles of B? You need one, the molar mass of A. And then you can go from moles of A to moles to B using coefficients of A and B from your balanced equation. EQN is short for equation, of course. So how do you go from moles of B to grams of B? You need the molar mass of B. So this is something we've seen before quite a few times, and this is your normal stoichiometry, but not the stoichiometry of solutions. So what do you do in solution stoichiometry? Here's what you do. You go from, you want to go from the volume of A usually to a volume of B. The direct is hard, and please don't use C1V1 equals C2V2. This is a rather simple way of looking at things. It only works for one type of reaction, and that's where the moles of A equals the moles of B. If they don't equal, this doesn't work, so don't use this. Okay, and they teach this on things like Khan Academy and sometimes in high school chemistry. We want to use a more sophisticated approach. Okay, so still in these reactions, the connection between A and B are the moles, and that's from a balanced reaction. So here we want to go from a volume of A to moles of A, and how do you do that? Well, you need the molarity of A, because if you have the molarity and the volume, you can get the moles, because concentration times volume would be moles. How do you go from moles of A to moles of B? You need the moles of A and B from a balanced equation. And how do you go from moles of B to the volume of B? You need the molarity of B. So that's how you do it with solutions. Now here, we can also mix it up. So perhaps we want to go from grams of A to milliliters of B. The direct, again, is very difficult. So how would we do this? Well, the connection is still moles of A to moles of B from the balanced reaction. So how do we go from grams of A to moles of A? You need the molar mass of A. Moles of A to moles of B is the moles of A and B from a balanced equation, as normal. And then how do you go from moles of B to milliliters of B? You need the molarity of B. So what we're going to see is this being applied in a problem. So here's the problem. Metallic zinc reacts with aqueous hydrochloric acid. And here's the balanced reaction. Zinc solid plus hydrochloric acid gives you zinc chloride and hydrogen gas. This is the reaction you should have seen when you put the penny in vinegar. You should have seen a little bubbling at the edges of where you had scraped the penny against the concrete, and you see the silver color inside. And if you leave it in the vinegar for about 3 hours, you see these tiny little bubbles coming off of the edge of the penny. Okay, so I'm going to move this up just a little bit. What volume of 2.50 molar hydrochloric acid in milliliters is required to completely consume 11.8 grams of zinc? So we can start with our 11.8 grams of zinc. That would be the grams of A. We're going to turn that into moles of zinc. And then we're going to take the moles of zinc and turn that into moles of HCl. And then we're going to turn that into liters of HCl using the concentration. Now, since they want the answer in milliliters, we're going to have to convert this into milliliters of HCl. Okay, so what we have here are 1, 2, 3, 4 problems. And we could do this as 4 problems, or we could do it as 1 problem. So let's do it as 1 problem. So I'm going to start with 11.8 grams of zinc. And to get the moles of zinc, I'm going to multiply by 1 mole of zinc. And I'm going to look up the molar mass of zinc. I don't recall what it is. I want to say it's 55, but I could be wrong. No, it's 65.38. 65.38 grams of zinc. And then I want to convert that to moles of HCl. So we have up here from the balanced reaction, 2 mole of HCl to 1 mole of zinc. And then I want to convert that to liters of HCl. So I'm going to go ahead and use the concentration of my hydrochloric acid. So this is 2.50 moles of HCl per 1 liter of solution. So I'm going to put the 2.50 mole of HCl on the bottom and 1 liter of solution. And that's, of course, HCl solution. And here, that would give me my answer in liters because everything is canceled out up until now. So boom, 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 boom. I've left with liters of solution, but I want milliliters, so I'm going to multiply by 1,000 milliliters of solution per 1 liter of solution to get the final answer. And then, of course, estimate. So let's take a look. How many times is 11.8 going to 65? Well, this is pretty close to 12. 12 goes into 65 times, so I'm going to say that that's 5. 5 times 2.5 is like $2.50 5 times over, so that's $12.50. And then 2 will go into $12.50 about 6, 7 times, okay? And then I have 1,000 divided by 7. And so 7 goes into 10 one time. So I'm going to say around 1,300 milliliters, roughly. Excuse me, 130 milliliters, roughly. So that's just a rough guess. And let's see what we get. So I'm going to clear this and clear it again. So I have a nice blank screen. 11.8 times 2 times 1,000 divided by 65.38 divided by 2.50, and we get 144, because I'm going to just, well, here, I'm going to go ahead and change this into flow. And you can see we get 144.38. 3 zig figs, 4 zig figs, infinite, 3 zig figs, infinite. So our answer is going to be 144 milliliters of solution. Okay, now sometimes instead of writing solution, I do something like this. 11.8 grams of zinc times 1 mole of zinc over 65.38 grams of zinc times 2 mole of HCl to 1 mole of zinc. So everything so far has been exactly the same. And then here I'll put 1 liter of HCl and 2.50 mole of HCl. So how do I know that this is referring to a solution? Well, because the liter tells me that it's probably a solution. Solutions are measured in volumes that are usually liters or milliliters. Now, what would be even better is if I put HCl solution. And then if I multiply by 1,000 milliliters of HCl solution over 1 liter of HCl solution, you'll see what this comes out with is 144 milliliters of HCl solution. And so I get that HCl into my answer too. So it's okay to not use HCl here because this is really referring to one solution here, the HCl solution, but it's okay to put it in to be more instructive. Okay, so here's an example. Stoichiometry in a solution. Let's see if we have another problem here. And I believe we do. So here's another stoichiometry of reactions in solution. Unless you're from New York, in which case I think it's called a stoichiometry. Stoichiometry of reactions in solution. What volume of 0.109 molar HNO3, nitric acid, in milliliters is required to react completely with 2.50 grams of barium hydroxide? And here is the reaction. So what I'm going to do is I'm going to cover this up down here and show my work on this piece of paper. And I'm going to shove this up just so that we can see the problem and give myself a little more space to write. So our goal is to get the volume of nitric acid, and we're going to start with 2.50 grams of barium hydroxide. So naturally, I'm going to start with my 2.50 grams of the barium hydroxide, and I'm going to convert that into moles of barium hydroxide. And then that's going to be converted into moles of nitric acid. So that's always the key of going from one thing to the other. You go from moles to moles using the balanced reaction. And then I'm going to use this concentration to go to liters of nitric acid, because molarity is moles per liter, not moles per milliliter. And then finally, I can go to milliliters of nitric acid. So I'm going to start off with 2.50 grams of barium hydroxide and multiply by 1 mole of barium hydroxide. And here I'm going to have to figure out what that amount is. So a barium ion is 137.32. 137.32. So that's 1 barium, and actually it's 3,3. And 1 oxygen is 16, so 2 of them would be 32. And then 1 hydrogen is 1.008, so 2 of them would be 2.016. And so the molar mass of barium hydroxide is 171.35 grams. Now, I did round this off, but the reason I did that is because when I round it off, this has 5 zig figs and this has 3, so this has more significant figures than that, so I don't need to carry an extra digit around. Now I'm going to multiply by, according to this, 1 mole of barium hydroxide. Oops, I forgot to write mole. So 1 mole of barium hydroxide. And then on top, we have 2 moles of nitric acid. So 2 mole of nitric acid. Now, I want to go to liters of nitric acid, so I'm going to use this molarity. And I'm going to put the 1 or 0.109 moles on the bottom so that it cancels with its moles on top. And this is for 1 liter of nitric acid. And here, just to be very clear, I'm going to write nitric acid solution. So SOL is short for solution. You know that we use a lot of abbreviations in chemistry. Okay, so what do we do next? We multiply by 1,000 milliliters of nitric acid solution to 1 liter of nitric acid solution, and we'll get our final answer here. So I always like to estimate, so I'm going to do that again. So here, it's kind of interesting. 0.109 means 1/10. Now, 1 will go into 1,000 times. A tenth will go into 1,000 10,000 times. So now all of a sudden I have 10,000 with these 2 numbers here. I don't really like that because I don't like to work with 10,000, but I'm going to do it anyways. So I've got 10,000 times 2 is 20,000. 20,000 times 2.5, well, 2 times 20,000 will be 40,000. So we're talking about 50,000. 50,000 divided by 171. Boy, that's a tough one. But what if I do 50,000 divided by 200 and round that up? So I take these two zeros off and these two zeros off, and I basically have 2 into 500, which is 250. Now that isn't 200, it's 171. 200 goes in 250 times, so 171 might very well go in 300 times. So I expect the answer to be somewhere around 300 milliliters for the final answer. So let's take a look and see what we get for our final answer. Okay, grab this. There we go. Okay, so clear 2.5 times 2 times 1,000 divided by 171.35 divided by 0.109, and then that's it. And we get 267.70, and it looks to me like based on the 2.50 and the 0.109, we're going to get three significant figures out of this. So we're going to write 268 milliliters of HNO3 solution. And there is our answer. Okay. So that's another example of a titration, a fundamental of titration type problem. Let's take a look at another problem here. So I'm going to shove this up like this so we can see this example. What volume of 0.750 molar lead nitrate in milliliters is required to react completely with 1.0 liters of 2.25 molar sodium chloride solution? Here's the balanced reaction. So I'm going to go ahead and start with 1 liter of my sodium chloride solution. Now you might be wondering, why am I starting with this? Well, this is a concentration, which means it's a ratio of moles per liter. This is a concentration, which means it's moles per liter. And this is really just liters. Normally, I like to start with the thing that is not a ratio and convert that thing into other things. So I'm going to write out my little scheme here. I'm going to go from liters of sodium chloride to here, using this concentration, to moles of sodium chloride. Because with this concentration, I can go between moles and liters, or liters and moles. So here I have liters, I can go to moles. Then I can go from moles of sodium chloride to moles of lead nitrate. And we should call that lead 2 nitrate because the charge on the lead ion is a +2. Now, what can we do for the moles of lead 2 nitrate? We can go to liters of lead 2 nitrate, and that's solution. But I'm not going to write solution because we have liters here. And because we want milliliters, we then need to go to milliliters of the lead 2 nitrate solution. So here's the pathway all written out. All we have to do is fill in for the arrows a conversion factor. So let's do that. 1.00 liters of sodium chloride solution times the concentration is 2.25 moles per liter. So here I'm going to put 2.25 moles of NaCl per 1 liter of NaCl solution. And you can see why I really like to abbreviate solution. That would just make things very much longer if I wrote out the word solution. And then times, to go from moles to moles, I'm going to have 2 mole of NaCl and 1 mole of lead 2 nitrate. And then I want to go to liters of lead 2 nitrate. So I'm going to use this concentration, and I'm going to have 1 liter of lead 2 nitrate over 750 mole of lead 2 nitrate. Okay, and then finally, we're going to multiply by 1,000 milliliters of lead 2 nitrate. And here I should put solution and solution. Oh, not solution here, solution there. 3, and then solution per 1 liter of lead 2 nitrate solution. Okay, so time to estimate again. Let's see, 0.750 is like 75 cents. 75 cents will go into $2.25 3 times. 3 times 1,000 is 3,000. 3,000 divided by 2 is 1,500. So the answer should be 1,500 milliliters with 3 zig figs. So let's see what we get here. So I'm going to clear this, and we're going to do 2.25 times 1,000 divided by 2 and divided by 0.750, and we get 1,500. So how do we write 1,500 with 3 significant figures, which is what we need? Well, 1,500 milliliters of lead 2 nitrate solution isn't going to do. So what we want to do is we want to move that decimal over 3 times to get 1.5, and we're going to put 1 0 after the 5 so that we have 3 significant figures. And we're going to write times 10 to the 3rd. Now I move the decimal over 3 times, and because I moved it over 3 times, the exponent on 10 is a 3, and it's a positive 3 because the original number is greater than 1. And this is going to be milliliters of lead 2 nitrate solution. And there's your answer. Okay, thank you for listening to the fundamentals of titrations. And you should be looking forward to the next video.